Probably one of the most classic eruptions in human history was the eruption of Mount Vesuvius in 79 AD.
We had scarcely sat down to rest when darkness fell. Not the dark of a moonless or cloudy night, but as if the lamp had been put out in a closed room. It grew lighter, though that seemed not a return of day, but a sign that the fire was approaching. At last, the cloud thinned out. The sight that met our still terrified eyes was a changed world, buried in ash like snow.
My name is Jim Webster, and I'm a curator here at the American Museum. I'm the curator of mineral deposits, but it also bridges into volcanology. Since I've been at the museum, about 28 years now, I've been fortunate. I've visited at least several dozen volcanoes around the Earth, but I've focused most of my research attention on two particular volcanoes, Mount Vesuvius, Italy, and Augustine volcano in Alaska. Mount Vesuvius is along the Bay of Naples. It has erupted roughly 20 times since the last huge eruption in 79 AD. The last eruption of Mount Vesuvius was at the end of World War II.
Up from the crater of 4,000-foot-high Mount Vesuvius rise towering clouds of smoke and volcanic ash.
Now, Naples and the surrounding areas have 2 to 3 million inhabitants. Probably 600,000 live within what's called the red zone, the danger zone. Augustine volcano is actually a volcanic island. It's located up away from populations in Alaska. It is about 200 or so kilometers from Anchorage, and Augustine is the most active volcano in the eastern Aleutian chain. It's erupted 7 times in the last 200 years, most recently in 2005, 2006. Unfortunately, I and a colleague here were able to go and do sampling in the summer after that eruption settled down. All of these are drawers full of Augustine samples. What we want to do to actually understand nature is to begin really with natural materials. So this is a volcanic rock from Augustine. There are dark and light crystals. So these are minerals that crystallize out of the liquid rock. Sometimes as these crystals grow, they may trap some of the molten rock inside of them.
The good part is it can preserve the information exactly when that melt was trapped. So we can know what kind of compositions and combinations of pressure and temperature relate to a certain type of eruptions. My name is Shuoding. I'm a postdoc in the museum, and my research is to investigate the pre-eruption stage of a volcano. By conducting experiments, we can compare our experimental results to the samples produced from a historic eruptions. And if we know something about the composition and the conditions, we can connect our study to what happens inside the Earth. That might be able to help predicting eruptions.
We use expanding gases in an internally heated combustion engine to drive pistons and move cars. We use expanding steam and turbines to drive electricity. And in volcanoes, expanding gases drive explosive behavior. So highly explosive magmas have higher gas content.
It seemed to happen in an instant. The whole top of the mountain, tons of ash, rock, and ice, rocketed into the stratosphere.
Just like when you pop the top on a bottle of seltzer water and the bubbles form. But there's another factor, and this gets into the chemistry. The most abundant element in all magmas is oxygen. The second most abundant is silicon. The more silicon and oxygen in the magma, the more viscous, sticky, thick that magma becomes. The more viscous the magma, the more difficult for it to release its gases. So if it's gas charged, basically there are billions and trillions of little tiny gas bubbles. Each one has an explosive force, but there's so many that during the course of a single eruption, huge amounts of energy can be released during these eruptions. And both Augustine volcano in Alaska and Mount Vesuvius in Italy, they're both very gas-charged magmas. But there's something different between Vesuvius and Mount Augustine. Vesuvius is higher than sodium and potassium. The more sodium and potassium that's inside a magma, it tends to break up that structure, it weakens the magma. So more in Vesuvius, less in Augustine, and they actually have very different eruptive histories. Augustine, the last 200 years, and it's been every 10, 20, 30 years has been an eruption. Whereas at Vesuvius, it's been very different. So for a rock sample from a given eruption, say the 2006 eruption, we can analyze its chemistry, but then we need data to compare that to, and that's what we do here in the lab.
I cook my rock. My experiment is mainly to replicate the conditions inside the Earth, like 10 kilometers depth at the pre-eruption stage.
We'll take a powdered material of some either natural rock or a synthetic equivalent, and we'll put them in a little capsule of gold. We use gold because it's relatively chemically inert. We'll add water, we'll add carbon dioxide, we'll add sulfur, and we'll add chlorine or fluorine in some form.
And I sealed it to make sure nothing escaped. And then I put my capsule in one of these bombs. The bomb it's like a pressure pot. You put things inside and pressurize it and heat it. I run all my runs at 800 degrees C. It's hot enough to melt the rock I'm using, but not hot enough to melt my capsule.
Then let it sit and cook, typically days to weeks. Sometimes it might be a month for a given experiment.
And then turn off the heat, let it quench to a rock again. I will analyze it, analyze the composition, and then we can compare the composition of the rocks from a historic eruptions to my experimental results to see at what condition that nature sample was produced.
Mount Vesuvius was on a 40-50 year cycle. So the issue now, because it's been almost 75 years, is Vesuvius going into a resting period where potentially the next big eruption might be a huge eruption. Or is it just running a little bit late? We're putting all this together, and I think we'll have a really good chance, from one explosively erupting volcano to another, to understand prior eruptions and hopefully forecast future activities.